was thinking at 10:25. It's 35 minutes. You can easily spend 20 to 20 minutes just getting your baggage checked.
We on the air? Okay, we're on the air. Okay, first of all, let me remind you, because people have just been asking me, all the syllabus and all the homework can be downloaded from the website, course website. And next time I'll be discussing homework 0. So you should download it and bring it with you. And spend some time looking at it in advance, because it'll be much better if you know what I'm talking about in advance rather than looking at it for the first time during the class. And then after there's questions, after everybody seems to understand it, then we'll make it due about 3 weeks after that. So where we stand now is I assigned homework 1, the birthday problem. Last time I said it was due in a week and a half, which would mean it's due in a week from today. And are there any questions about that? I'm recommending that you do it in BASIC, and if you want to know how to get BASIC, then you send me an email just saying send me BASIC, and I'll send you back a file with some directions. Is there a question there?
That's what I was going to ask, where you get the BASIC and recommend.
Okay. There's various versions of BASIC. This, what I'm using is QBasic or Quick Basic. There's one called UBasic that in fact is pretty powerful. It's like Fortran. But for our purposes, the simplest BASIC you can get is good enough. Okay, remember also what the rules for the homework are. You're supposed to adapt the code, which means that you change it slightly so it does what's asked for. And that means that instead of printing out the answers for 10,000 cases, you print out the answers, you run it for 10,000 cases, so you put it in remove it from what is now an infinite loop to a loop that goes through 10,000 times, and then you print it for the particular values asked for. I think there's 11 of them, 1, 2, 3, 4, 5, 25, 50, something like that. So you just print it out for those values. So what I should see is the printout of your actual code that you used, the printout of the result of that code, whatever's on the screen, plus then you take those results and you copy them over in a table on the cover sheet of the homework. So once you understand once you've done this once, this is then easy. The actual content of this homework problem is essentially nothing. It's just getting used to running it and putting it in the proper format. So any questions about that? Any questions about anything? So the last time I said that the assignment was to read the preface and pages 1 through 21. So now I want to start talking about that. So as I go along, what I'll try and do is tell you where I am in the textbook. And the way I'm going to do it is somewhat similar to what's in the textbook, but not exactly the same thing. So I'm going to start with section 1.2, which is called sample space and events. And the basic idea is that we're going to be talking about probability modeling. So you're going to imagine some real phenomenon, and then you're going to a real setup, and then what you're going to do is you're going to describe that in a mathematical model which abstracts from the reality the important pieces. And it has to be simple enough so that you can manipulate it, but rich enough so that you can use it to predict what would happen if you did something else. So to start with, probability really is concerned with the frequencies with which certain things happen. So you have to define what those things are that you're concerned with, and you have to define what you mean, exactly how you're going to model frequencies. So we start off with the idea of sample space. So this is section 1.2, sample space and events. And we'll call the sample space S. And what that means is you've got this set of points, the sample space, and these points represent the atom, so to speak, the smallest thing that can happen when you perform this experiment. And then, sets of these points then are the things that can happen, or what we call the events. So let me, rather than trying to be abstract about it, let me give an example, and I'm going to use this particular example over and over again throughout the course. So here's the basic idea. I'm going to look at the case where the experiment is that you're going to be rolling 2 dice. So I'm going to represent the sample space by these points. So let me call the horizontal axis x1. Okay, so x1, what that is going to be is the face value of die 1. In other words, I've got 2 dice. The plural of die is dice, D-I-C-E. That's one of those meaningless or incomprehensible rules for English. I don't know why that is. But anyhow, we have these 2 dice. We're going to roll them, and each die has 6 faces. Each face has a number on it, 1, 2, 3, 4, 5, 6. So let x1 be the face value of die 1, and x2 will be the face value of die 2. So the dice look identical to you, but they know who they are. They're separate dice. You could imagine that they're colored. One might be red and one might be blue or something like that. But I don't care. I'm just calling them die number 1, die number 2. And die number 1 can take 6 possible values. So here they are. 1, 2, 3, 4, 5, 6. And die number 2 can take 6 possible values. Also, 1, 2, 3, 4, 5, 6. So I'm going to make the points in the sample space these 2 tuples, like this. x1, x2. So for example, this corresponds to the event that when I roll the 2 dice, die number 1 is a 1 and die number 2 is a 1. Snake eyes, as they say. Or I could get 2-1, or 3-1, 4-1, 5-1, and so forth. So each of these points is a point in the sample space. So this is part of my model, because what I'm claiming here in my model is that there are only 36 things that can happen, 36 elementary events. So let me write that down. We're talking about what are called elementary events. And these are like, I'll put this in quotes, atoms, in the sense that it's they're the smallest possible events. So when I say that I have these 36 points in my sample space, what that means is that that's all I'm considering in my model. So I'm not allowing other things to happen. I'm not saying that, well, when I roll the dice, maybe one of them stands on a corner, or falls off the table, or turns into powder or something like that. It's not that those things couldn't happen. I'm not saying they're impossible. I'm saying that they're out of my model. So once I have this set of points, now everything is determined in terms of these things. So, for example, I could consider, these are the basic sample or events right here. Let me rewrite it. So one possibility is x1, x2. These are the elementary events. But from that, I can make other things. For example, I could ask for the value of x1. I don't care about what the second die is. Or I could ask for things like the sum of the dice, which is a common question. I could ask, what about x1 plus x2? So, for example, if I wanted to worry about the sum of the dice equaling 7, that means that would consist, that event, that the sum of the dice equals 7, would consist of the points, all of which had the property that if I add up the value of x1 and the value of x2, that their sum is 7, which would be this point, which is 1, 6, this point, 2, 5, that, and so forth. So you can see that events then are sets, and the basic idea is that you start off by defining some sample space, which has the smallest or the elementary events, and then from that you predict what would happen in terms of more complicated events. So here's an example. I'm adding these so-called random variables. But let me give you an example of a much more complicated question, which is one that we'll get to later on in the course. So you can look at this as being a place where we're going. So keep something like this in mind. I start off and I say, okay, I'm going to roll 2 dice, and these 36 outcomes or events, those are the things that can possibly happen. And based on some assumptions, which we'll get into, about what the probability is at each individual point. Probability means frequency, and I have to define that. But each individual point occurs with a certain frequency, meaning that if I were to roll the dice under identical conditions over and over again, then each one of these events would occur a certain fraction of the time, with a certain frequency, and the notion of probability is going to be a model of the observed frequency. So if I tell you what the fraction of time or frequency is with which this point occurs, and that point, then I'm going to tell you these 36 frequencies, but then I might want to ask a question that's much more complicated. So here's the kind of question I might ask. Suppose that you're playing the game of craps, and in craps, these are the rules. Don't worry about them. We'll write them down later. But these are the rules of craps. The player rolls 2 dice, and if the sum of the dice, which is called the value of the roll, if the value of the roll is 7 or 11, he wins the game. If it's 2, 3, or 12, he loses the game. If it's anything else, that something else is called his point. Then he rolls the dice continually until either he gets his point or he rolls a 7. If the point comes first, he wins the game. If the 7 comes first, he loses the game. If anything else happens, he just rolls the dice again. So you can see it's very complicated because, in fact, you can't even tell in advance how many times he's going to roll the dice. So the question then is, if I start off with something simple and I tell you that when I roll 2 dice, I have 36 possible events, there they are, and then ask the question, based on this, what's the probability if I play this game called craps that I will win the game? What I want to do is I want to be able to answer that based on only this plus the rules of probability, which we haven't stated yet, but that's where we're going. Okay, so I'm going to go back and forth. I'll be using this kind of example all the time. Now, the book gives lots of examples, and so I suggest that you read them. But the book has more information and makes things more difficult than is actually necessary. So if you read the book and you have questions, just raise the questions in class. But I would say that if you have trouble with it, don't worry about it as long as you can understand what I'm talking about in class. Okay, now, another issue is that the way that the book handles this at first is it talks about these sample spaces and events in some set theory. So the events, you could talk about an event in terms of, in verbal terms. That is, events are the things that can happen. But in order to make the subject more abstract, which makes it at the same time more difficult and more easy, what you do is you change the events into something else which are called random variables. So a random variable is an event or is a numerical value that is assigned to an event. So for the purposes of being able to discuss this mathematically, what we'll do is we're going to change the events, which are stated in verbal terms, into numerical values. And then we talk about a random variable being the numerical value rather than the event itself. And when we do that, then we don't have to worry about what the verbal description is. We can simply start talking about the values that the random variable takes. So for example, the way I wrote it here is, I said x1 is the face value of die 1. So the textbook wouldn't say that because the textbook doesn't talk about random variables. It simply talks about the event, which would be the face value of die 1 takes a certain value. What I say is x1 takes a certain value. Now that may seem like a minor point, but the book discusses what are called random variables. So let me write that word down here. Random variable, sometimes called RV, or I don't know, recreational vehicle. So a random variable is a function that assigns numerical values to events, and events are sets. So the result is that this can get mathematically complicated because if you want to be rigorous about this, then you have to what possible sets are eligible to be given measures by functions. So this becomes complicated. So if you're going to write a book that is technically correct, you have to first worry about events and set theory, and then later on you worry about random variables. But from an intuitive point of view, this is really simple. So what I want to do is I want to talk in terms of random variables right at the beginning. So maybe this is something we should mention. Nobody likes this book, but nobody likes any book that I've ever seen that makes any sense, because this is a very mature subject. It's been in development for a long time, and so there are very good, precise mathematical treatments. On the other hand, so mathematicians love this stuff. On the other hand, there's the fact that it's extremely important, so that means that everybody has to know it. So if you take a course, if you take a degree program in psychology, education, social sciences, doesn't make any difference what it is, almost. You have to take some kind of course in statistics, which is an application of probability. So the result is that if you're an engineer and you're supposed to really sort of know what's going on, then in order to take an accredited course, or a course that's accredited for an engineering or computer science program, you have to take a course like this that requires calculus as a prerequisite. But of course, if you're an education major or some kind of social science major, you may not know calculus. You can't require everybody to take a year of engineering calculus. So that means that they have to teach this subject on a level in which actually it's a cookbook course. You can't possibly understand it because it presumes knowledge of mathematics that the student is presumed not to know. So the end result is that you actually have two kinds of books. It's sort of like a divergence. On the one hand, you have very detailed, complete, correct books which have the truth, which is an example this book does, but it's difficult to read because it has too much. And it's too abstract for most students unless they're interested in mathematics for its own sake. Then you have all the books that are written for education majors, business majors, and they have lots of examples, lots of chit-chat, many colors, boxes drawn around the formulas and all of that kind of stuff. But they tell you nothing, or actually they lie to you because they can't tell you the truth because it's too difficult. So these are big, thick cookbooks. Students like those because when you open them up, you can read it, you can understand what it says, unless you actually think about what it says. And if you really think about it, then you realize it makes no sense, but what are you going to do? So anyhow, this is a more technical course, so there doesn't seem to be a book in the middle. So for that reason, we have to stick with a book like this, which is actually very good if you can read it, because everything it says is true. But you have to be able to handle the mathematical notation and fight your way through things that are maybe more detailed than you're really interested in. So actually, that's going to be my role, which is to try and use the book as a guide, but explain it as I go along. So one of the reasons, or the reason why the author doesn't use random variables until the end of the book is that he's trying to be correct, and you can't really use random variables until you've discussed a lot about set theory. But pretty much for applications, that's not important. So I'm going to go back and forth between them. I don't really think there'll be any trouble. Anyhow, that explains somewhat, I think, why some of the examples that he gives in the book are maybe not too helpful. But if you can read them and understand it, that's fine. Okay, so in any event, what it means is that when I talk about events, events are sets, and that means that I have to understand set theory a little bit. So event is a set. So that means I have to understand things like union, intersection, complement, and so on. But the set theory that you need for probability at the level that we're doing is pretty slim, and I think everybody already knows that. So I'm just going to assign that as reading. It's a review, and you'll see that when we use it, it's at a minor level. Also, one way that we can analyze this stuff is by what are called Venn diagrams. And the Venn diagram, that's a picture like this. Here's some set A, and here's some set B, and then this set right here would be, for example, the intersection of A and B. So in mathematics, when you want to prove something about sets or anything, the conventional rule is that you're not allowed to draw pictures. That's a no-no. But actually, pictures are very helpful, and so if you're not trying to be rigorous, but you're just trying to understand things, pictures are sufficient. And for our cases, we're not proving things, we're trying to understand things. So we only prove what's necessary for understanding. So anytime a Venn diagram is helpful, use it, because there's not going to be any proofs in this course. There's just going to be derivations and applications of formulas. And as long as you understand the essence of those things, that's what you need. So he mentions Venn diagrams on page 7. And then there's a lot of stuff here which I would say you should read in a sort of skim over it, but I wouldn't dwell on it. And then I get to page 11, which is called axioms of probability. So this is where we start. Okay, so let me erase this here because I need room. So we're talking about in the book is called axioms of probability. And let's see, that's section 1.3, page 11. The basic idea here, remember, is that we're making this model, and we want to be able to develop this theory of probability, which is actually the mathematical theory of frequencies. We want to be able to develop that in a systematic fashion so we understand what's going on. So in order to do that, what you would like to do is make some assumptions, which are the minimum assumptions you can make that make any sense, and then based on those assumptions you develop this theory. Of course, in our case, we don't have to overdo it in terms of the rigor, but still we should understand what's going on. So on page 11, he starts developing these axioms of probability, and in typical mathematical statement, he states these 3 axioms on page 12. But he doesn't really motivate them. So let me see if I can motivate why he's going to make these axioms. Okay. So first, I want to talk about frequencies, because remember that the purpose of probability is to be able to describe and predict the frequencies with which certain events would occur if certain experiments are performed. And keep in mind, the experiments I'm talking about at the beginning are things like rolling dice or tossing coins. You can toss a coin and you can get heads or tails, and you want to know things like how likely is it if I toss a coin 100 times that I'll get more than 60 heads, things like that. Okay, so to begin with, we'll talk about frequency, and I'll make this definition. Here's a frequency with which an event occurs. So I'm going to call it f sub n of a. So the n is, well, f is frequency, so frequency, or fraction of times that something happens. And n is the number of trials. And A is the event. So what I'm asking is, what's the frequency with which event A occurs in a certain number n of trials? So A could be, for example, rolling a 7 when I roll 2 dice. And then I could say, what's the frequency that I would expect that if I roll 2 dice over and over again under identical conditions, that what fraction of those rolls would result in a 7. Or if I'm tossing a coin, if I toss a coin over and over again, what's the fraction of tosses that result in a head, say? Then the event A would be a head. So I've got this event, which is some set that's well defined, and I say I'm going to perform this experiment over and over again, and I'm going to measure the frequency with which the event A occurs. Okay, so this is the way you would define it. I would say the numerator is the number of times that A occurs, and the denominator is the number of times I conduct the experiment. So N of A is number of times A occurs. So the frequency of A is the ratio of the number of times it occurs to the total number of times I conduct the experiment. Now, the idea of probability is that probability is supposed to represent frequency or model frequency. So what I want to do is I want to list some of the properties that frequencies have, and then when I set up my axioms of probability, I will specify that probabilities must have those same properties. And then once we do that, we're sort of removed from the frequency area, and we're looking at these probabilities, which are then mathematical things. Then we manipulate the probabilities, then we interpret the results as frequencies. So you see this over and over again. It may sound abstract at this moment, but it's pretty simple, at least at the beginning. Okay, so what are the properties that frequencies must have? So these are obvious. It's obvious that what I'm going to write down is true. First of all, the frequencies must be non-negative. Right? You can't have a, if I'm going to take a ratio of the number of times something occurs to the number of times I conduct the experiment, I can't come up with a negative number. The second statement is that the frequency of S must be 1. Okay, so now what does that mean? This says I'm going to conduct the experiment over and over again, and S is a sample space. In other words, S is the union of all of the points, everything that can possibly occur. So if S is the event that includes everything, then the fraction of time something occurs that's in the set of every possibility, that of course must be 100%. So for example, if I wanted to say I'm tossing a coin, and I fix my sample space as being 2 points, heads or tails, then the frequency of S would be the fraction of time when I toss my coin that I get either a head or a tail. And of course, if those are the only things that are possible, that must happen 100% of the time. Okay, so frequencies must be non-negative, and the frequency of the set of all possible outcomes must be 100%. And the third thing is basically the critical one, and that says that if A1 and A2 are mutually exclusive, then the frequency, let me write this over here, although I'm going to have to erase things. The frequency with which I get either A1 or A2, in other words, the frequency of the union, is equal to the sum of the frequencies. Okay, so let me prove that or argue that for frequencies. So what does this say? It says that I'm going to perform this experiment under identical conditions n times, and I have 2 events which are called A1 and A2, and they are mutually exclusive. So mutually exclusive means that their intersection is empty. For example, I could say as my events, looking at the dice, I could say event A1 is the event that I roll a snake eyes, and event A2 is the event that the sum of the dice is a 7. Now, if I roll a snake eyes, I don't get a 7. If If I get a 7, I didn't roll a snake eyes. So those events are mutually exclusive. Okay, now if they're mutually exclusive, then the frequency with which I get either one or the other is the sum of the two frequencies. Okay, so why is that? Let's see. Here's the frequency of A1 or A2. By definition, that's the number of times I get either A1 or A2 divided by the total number of times I conduct the experiment. But now, if the events are mutually exclusive, that means if one occurs, the other one does not, there's no overlap, no intersection, then the number of times I get one or the other is obviously equal to the number of times I get one of them plus the number of times I get the other one. In other words, the number of times I'm going to get either a snake eyes or a 7 is the number of times I get snake eyes plus the number of times I get 7. Because if one occurs, the other one does not. Okay, so this equal sign is because of the assumption that the events are mutually exclusive. But now by ordinary algebra, that's the same thing as n of A1 over n plus n of A2 over n. But then by definition, that's the same thing as the frequency of A1 plus the frequency of A2, and so this statement is obviously true. Okay, so what I did here was I said the whole purpose of this subject is to be able to describe the phenomena of frequencies. And so what I'm going to do is I'm going to, first of all, define, when I mean frequency, what happens. Those are the events that can happen. And then I define the frequency of the event as being the ratio of the number of times the event happens divided by the number of times that I conduct the experiment. And then I say, now, if I'm going to make a mathematical model of frequency, and I'm going to call frequencies probability, then what that means is these probabilities must have certain properties. So what are those properties? Well, looking at frequencies, here are three sort of obvious properties. First of all, a frequency can never be negative. Second of all, the frequency with which something happens must be 100%. And the third thing is that if I look at two events that are mutually exclusive, that exclude each other, then the frequency with which I have either one or the other is the sum of the two frequencies. Now that seems pretty harmless, but it'll turn out that that's all we need in order to develop this whole mathematical theory. Okay, I wish I had another blackboard here, so I think I'll erase this piece here. So what I usually do is I write stuff down and then I erase it and say, are there any questions? But I'm trying to get over that, so I should ask, are there any questions, and then erase it. So are there any questions here before I erase this? Okay, so I'm going to erase this proof. And let me state the conclusion right here. Then the frequency of A1 or A2 is equal to the frequency of A1 plus the frequency of A2. Okay, now let's look at the axioms of probability, which from a mathematical point of view don't necessarily have anything to do with anything. But of course, from a physics point of view, remember this is a physics course here, the probabilities are supposed to be frequencies. So what I want to do is I want to come up with properties, or what are called the axioms, which are going to correspond to the frequency. They're going to model the frequencies. So here's statement number one. We're going to assign to each event A a probability. And then we're going to say that the probability of any event must be non-negative. Same as this. The second thing is we're going to say that the probability that we assign to the whole space must be 1. And the third thing is that if I have any two events that, or sets that don't overlap, so if A1 intersected with A2 is empty, that is, they're mutually exclusive, then the probability of A1 or A2 is equal to the probability of A1 plus the probability of A2. So I'm going to take these obvious statements about frequencies and I'm going to translate them into statements about probabilities. And here is my hypothesis. This is why I'm doing this. These are simply mathematical statements, but what we think is the following. Suppose I took the frequency of any event A, and I took the limit of this as n goes to infinity. In other words, I don't conduct the experiment a finite number of times. I conduct it over and over again under identical conditions. Of course, that can never happen because, well, first of all, I can't do anything an infinite number of times. And second of all, I can't do anything under identical conditions. I mean, at the very least, if I do something and then do it again, time is different the second time. The universe would have existed a few seconds longer when I conduct the experiment the second time as opposed to when I did it the first time. So it's just a concept that I'm going to imagine that I can conduct this experiment, toss a coin, roll dice, whatever it is, over and over again under identical conditions as often as I like. But if I could, everybody would seem to agree, I think, that these frequencies would stabilize. For example, if I'm tossing a coin, then even though on each individual toss, I don't know whether I'm going to get head or tail, if I toss it thousands of times, I can be pretty sure that approximately half of them are going to be heads and half of them are going to be tails. So what I'm going to hypothesize then is that if I take the limit of these frequencies, that they will in fact stabilize, and they stabilize to what we're going to call the probability. So since we're assuming that it would be true, if we could do this, that these frequencies in the limit as n goes to infinity correspond to some limiting value, then what I'm going to do is I'm going to model these limiting values by saying, well, what I'm doing now is I'm going to define a set, or which is the sample space and all its subsets. And then for every set, I'm going to define a function which assigns to that set a number, which is called the probability. So the probability is actually a set function because its argument is a set, and the probability then turns that set into a number. And that number is never negative. The measure, or the number, you could say that this measures a set. The measure of the set that includes every possibility is 1. And if I have two sets that don't overlap, then the measure of their union is the sum of their measures. Okay, so this is what's given in the book on page 12. Except that in page 12, the author doesn't really state very clearly that these things are exactly the same as these things, and that's why we're doing it, because he's a mathematician. Now, one other thing that's different in the book, again, just a mathematical detail, is that instead of talking about finite unions, he's talking about infinite. In other words, there's no necessary reason why I can't talk about the union of A1 and A2 and A3 and A4 and so forth. Yes?
In number 3, we want to say if A1 intersect A2 is going to be null, or like when...
That's right. This stands for the empty set.
Yeah, but I mean, it should be like, I guess, A1 intersect A2, right? If they don't intersect, right, then their union would be equal to their sum.
Right. If the intersection is empty, which means mutually exclusive, then this is true. And if it's not empty, then it's not true. In fact, we have to do something else. So in fact, what we're going to do now is, based on these really harmless-looking axioms, these harmless-looking statements, observations, we get these harmless-looking axioms. And from these axioms, everything else follows logically. So it's just a matter now of proving theorems. Of course, this is not a theorem-proof course, but the point I'm making is that suppose that you were really smart, like you were a computer instead of a person. If I told you these three things, then that's the end of the course, because everything else is a logical consequence of this, and the rest of it is just examples. I mean, that's not the way the human mind works. Human mind works is you have to figure out examples and then go backwards, and then you use the abstraction to try and understand it better and prove things. But all the content is already here. Everything that we're going to get in the future is simply an application of these rules. Okay, so let me say that, do it up here. So here's our model. Events correspond to sets, and frequency corresponds to probability. So, from a mathematical point of view, when you're in sets and probabilities, there's no necessary connection to anything. It's just pure logic. But the thing that drives this is that this is supposed to be a model of the notion of events and frequencies. And what it models is the idea, what it represents is the idea that frequencies are stable in that, and we don't know why this is true, if you think about it a moment, but what it means is that we have this observation that if we perform an experiment with several different possible outcomes over and over again under identical conditions, then the fraction of time that each particular outcome occurs is going to stabilize to some value, and so we call that the probability. So if you think about it, suppose you're tossing a coin. This is why this is very mysterious. I don't think anybody would doubt that if I take a coin and I toss it 10,000 times, that it's pretty likely that the ratio of the number of heads to 10,000 is going to be very close to 0.5. Anybody doubt that?
For an unbiased one, right?
Yeah, well actually unbiased is a definition, so it's sort of circular. But if you had a coin that physically, there doesn't seem to be any physical distinction between head and tail, then you would expect that this would happen. Of course, you can never prove it, because if you do it 10,000 times and it works, that's only one time. Maybe it wouldn't work the next time. If you do it an infinite number of times, well, you can't do it an infinite number of times. So this is already kind of fuzzy. But nevertheless, if you deny this, then you're really in the Stone Age, because if you don't agree that frequencies have some stability properties, if you don't agree there's any predictability, then you might as well throw all of science and engineering out the door. Okay, so let's agree for the sake of argument that if I toss a coin 10,000 times, roughly half the time I'll get heads and half the time I'll get tails. So what I would say then is that on any individual toss, the probability of getting a head is 1/2. But what does that mean? On an individual toss, you have no idea whether you're going to get head or tail. And just tossing it one time doesn't tell you anything, because when you toss it one time, well, you'll either get head or you'll get tail. Now, when you toss it multiple times, somehow or other, even though each individual time is unpredictable, if you toss it thousands of times, the result is predictable. But how could that be? Because the coin is inanimate. It doesn't remember what happened in the past. The coin doesn't say, let's see, I just got a bunch of heads, so maybe I should get some tails to make things balance out. The coin tosses are independent of each other. I'm just alleging this or asserting this. I mean, who knows? But it seems that on the one hand, the coin, since it's an inanimate object, has no memory of the past, and so every trial has nothing to do with any other trial. And yet, even though each individual trial is unpredictable, the more trials I have, the more predictable the results are. So you have this strange effect that if you know nothing, but you know nothing lots of times, you know something. So I don't understand that. But I know it's true, and we'll verify that lots of times in the course when you simulate something. Because when you simulate it, what you're going to do is you're going to perform the experiment, have a computer perform the experiment for you. Then you're going to compare that with what the theory predicts, and of course it's always going to work. Okay, so those are the axioms of probability, and now we have to do a little bit of mathematics, not very much, to get some theorems that come out of this, and then these are going to help us evaluate probabilities. And so we start off with simple probabilities, we toss some coins a couple of times, and then we get to much more complicated things like craps and things that are way beyond that, but surprisingly easy. Okay, so any questions up to this so far? All right, so now what the author does is he has some theorems, but he makes things look more difficult than they really are. So let me erase this stuff here. And list what some of these theorems are. It's sort of obvious. So first of all, notice that we have this sample space. So we start off and somehow we say, okay, we got this set of points which represent all the possibilities, everything that can happen when I perform the experiment. And suppose we have some set A, that's an event, which I'll just indicate like that. So A is the set of all of these points, so all the points that are not in A is the complement. And the sample space is the union of A and its complement. And of course, from the way I've drawn it, A and its complement are disjoint or mutually exclusive. They have no overlap. That is, the intersection of A with its complement is the empty set. Okay, so the first statement I want to make is this. Suppose I look at the probability associated with S. Well, we know that that's 1. But it's also equal to the probability of A or its complement, the union of A and its complement. Okay, so this is true by definition. This is true by axiom 2. Of course, I had the axioms here. I had to erase them because I don't have any space. Okay, that's axiom 2. This statement is just this definition because it's always true that a set and its complement adds up to the whole space. But then, since these two sets are mutually exclusive, that means that this is equal to the probability of A plus the probability of the complement of A. Okay, so this is axiom 3 right here. So that means that the probability of any event A is equal to 1 minus the probability of its complement. Or, equivalently, the probability of the complement is equal to 1 minus the probability of the event. So what this says is that, as a practical matter, if I want to compute probabilities, the first thing I should ask myself is it easier to calculate the probability of the event happening, or is it easier to calculate the probability of the event not happening? Whichever is easier, that's what I calculate. If I want this, and I can calculate this, I calculate that and subtract it from 1. So we'll see examples of this, but as a mathematical proof, this is no big deal, even though the author calls this a theorem. So in fact, this is theorem 1.4 on page 18. Theorem 1.4, page 18. Here's another one. Here is my sample space. And here I had some event A, and I'm going to go through examples of this soon with the dice, so it won't be so abstract. Okay, so here is A, and here's B. So A and B now are going to be general events. And the question I want to ask is, what's the probability that I get either A or B? And the answer is, it's the probability of A plus the probability of B minus the probability of the intersection of A and B. Again, I got to keep reminding you, right now this looks like a lot of theorems, but as you'll see when I apply it to these dice problems, there's nothing to this. So this, in fact, is theorem 1.6 on page 19. Okay, so why is this true? Let's use Venn diagrams. This says we want to calculate the probability or the measure associated with A and B. It's all the points in A or B, the union. So I could say, well, the probability associated with that is, first of all, the probability associated with this guy right here. But then, if I add up the probability associated with this guy, I've added this piece twice. So I have to subtract the probability associated with the intersection, and that is this value right here. Okay, so there's a Venn diagram argument without going through a lot of set theory. Okay, so that makes sense? Or I need one more thing, and then we'll go and look at and verify these things using the dice argument. Dice example. Now, what I've told you so far is what some properties of probabilities are, and I told you how I can represent events as sets. And again, I want to keep saying this because so far everything has been too mathematical. When I actually apply it to here, you'll see exactly how these things work. But I got to get to the point where I can make an application. Okay, now the thing I haven't told you is how I assign the probabilities in the first place. So I said, for example, that if I toss a coin, then I would say that the probability of head is 1/2 and the probability of tail is 1/2. But we got to be able to do more than that. So there's one particular case that's very important. It's the simplest possible case, and that is this. Suppose that I have n points. That is, I look at my sample space, and it consists of n points. I think I'll erase this stuff here. So here's my sample space. And it's got these finite number of points in it. And the author calls this capital N. So this is theorem 1.3 on page 16. Theorem 1.3, page 16. And what he says is that if S sample space consists of capital N equally likely events, then, okay, I got to explain what I mean by equally likely, but S is going to consist of these points, which I'll call x1, x2, x sub n. Those are the points in the sample space. There are a capital N of them. And if they're equally likely, then the probability of any particular one, the ith one, is going to be 1/n. Actually, in the book, the author calls these S. So let me use his notation. He calls the sample points S1, S2, Sn. And so this is the probability of Si, the ith point. Okay, so what is he saying here? He says, look, I have capital N points, and we know that the probability of the whole space must be 1, and since these points, the union of these points make up the whole space, that means that the probability, the sum of the probabilities in each point must add up to 1. And so if I want to say that they are all equally likely to occur, that means each one must have the same probability, and so therefore each one must have probability 1/n. So if my sample space consists of the 2 points heads and tails, say, for tossing coins, then if I assume that heads and tails are equally likely to occur, the probability of a head would be 1/2. There are 2 points in the sample space, and the probability of a tail would be 1/2. if I have two dice and I have 36 possible elementary events and each of them is equally likely, then the probability of each individual event would be 1 over 36. So when I say that they're equally likely, that's my assumption. I mean, how do I know that that's true? This is very circular. Because to say that the probability of a head is 1/2 is to say that if I toss the coin an infinite number of times, whatever that means, half the time I would get heads, half the time I would get tails. So we can't actually test this. But our intuition says, look, I got this physical situation. I got this coin. Now, when I toss it, there are two possibilities. We're assuming that I have to get either head or tail. I'm not going to allow it to stand on its edge or vanish into space or something like that. And therefore, the probability, therefore the frequency with which the heads or tails should occur, each should occur half the time. In other words, I'm just as likely to get a head as I am to get a tail. I don't really know if that's true, but I assume it's just as likely to get a head as I am to get a tail. And if that's true, then the probability of getting a head must be defined to be 1/2. If I roll the dice, and I've got 36 possible things that can happen, and I assume that it's just as likely to get a 1/1 as it is to get a 1/4 or to get 6/6, then every event, every one of those points must have the same probability. They must add up to 1. If they're all equal and there's 36 of them, each one must have probability 1 over 36. Okay, so that's going to be my basic setup. And from there, well, let me do some examples from that. Okay, so let's see. I have some examples written out here. I want to use the same ones. Okay. So going back to here, let's calculate some probability. Okay, so first of all, we're talking about dice, and I'm going to assume equally likely events. All right, so I got to really be more careful about that. What I'm assuming here is this. I'm going to assume that the probability that x1 equals some value I and x2 equals some value j is equal to 1 over 36 for I equal 1 through 6 and j equal 1 through 6. Okay, that's my assumption. Okay, so now, suppose I wanted to calculate some things. What's the probability that x1 is equal to 5? Okay, so I got these two dice. I'm going to roll them. Die number 1 has 6 possible outcomes. Die number 2 has 6 possible outcomes. I'm assuming that every pair is as likely as every other pair. So there are 36 possible outcomes. So the probability associated with each one of them must be 1 over 36. Okay, now I'm going to roll the dice and I'm going to ask some questions. What's the probability that x1 is equal to 5?
1.6.
Okay, well, first of all, let me calculate it several different ways. x1 is equal to 5. Here's my sample space. So here is the set of points that corresponds to the event x1 is equal to 5. Because I can get 5-1, 5-2, 5-3, 5-4, and so forth. So one way of doing it is to say, well, that's going to be the probability. Remember that the probability of this event is the union, or this event is the union of the points in the sample space that make that up. So and since those points do not overlap, the probability of the union is the sum of the probabilities. So this is going to be the probability of the event x1 is equal to 5 and x2 is equal to 1. Or x1 is equal to 5 and x2 is equal to 2, and so on. And the last one is going to be x1 is equal to 5 and x2 is equal to 6. And since those events are mutually exclusive, that's going to be the probability that x1 is equal to 5 and x2 is equal to 1, plus the probability that x1 is equal to 5 and x2 is equal to 2, and so on. Last one is going to be the probability x1 is equal to 5 and x2 is equal to 6. And then each of those has probability 1 over 36 by my original assumption. And since there are 6 of them here, okay, how many are there? There's 1, 2, 3, 4, 5, 6. That's equal to 6 over 36, which by arithmetic is equal to 1/6. Okay, so first of all, notice that here I worked it out directly, but I could have written this down by the theorem, because I could have said, okay, all I have to do is count the number of points in a sample space that correspond to the event in question, and there are 1, 2, 3, 4, 5, 6 such points. So I take the number of points that correspond to the event, divide by the total number of points in a sample space, and that ratio is the probability. But then by arithmetic, that turns out to be 1/6. And now you might say, well, that makes sense too, because suppose that originally, instead of defining my sample space to concern myself with 2 dice, suppose that I simply looked at 1 die. Because if I knew that I only wanted to care about x1, then I could say, now, suppose I looked at x1 and made a sample space for it. Well, how many different values can x1 take? Well, it can take 6 possible different values, and if they are all equally likely, then the probability of any one of them would be 1 chance out of 6. So this is consistent with your intuition, which is that if I have these dice with face values that are physically the same, that that the probability that any one of them will have any particular value is equal to 1/6, or the 1 value over the 6 possible values. All right, suppose I said, what's the probability that x1 plus x2 equals 8? Okay, so now in order to do this, what I have to do is I have to look at the points in the sample space that correspond to the sum of dice adding up to 8. So how can I get 8? Well, I could get 2, 6, I could get 3, 5, I could get 4, 4, and so forth. So in fact, I can draw a picture like this. And this set corresponds to the event x1 plus x2 equals 8. So I could calculate this probability by saying, well, it's the probability of 2, 6 plus the probability of 3, 5, and so forth. Or I could simply count 1, 2, 3, 4, 5. So there are 5 points in the event x1 plus x2 is equal to 8. There are 36 points in the sample space. So the probability that the sum is equal to 8 is 5 over 36. Now notice that in terms of events, with something as simple as this is easy to simply count. But notice what this is saying. I have these 2 random variables. That is, this x1 is the result of an experiment. That is, I have a die, and I roll it, and it has certain probabilities, and it produces certain values. And so this represents a random number, and this represents a random number. And then what I'm doing is I am adding up the random numbers, and I'm saying if I know the randomness associated with this one and the randomness associated with this one, I can combine them, and I can get the randomness associated with their sum. So later on in the course, we're going to be looking at random variables as things which are like numbers, except that their values are unpredictable, except in this probability sense. And then I'm going to say, okay, now if I have these numbers, well, ordinarily what I can do with numbers is I can multiply them, I can add them, I can take square roots, I can do all kinds of things with numbers. And if the numbers are deterministic, then you know exactly what to do. But if the values of the numbers are themselves random, then what are the values of functions of those numbers, like sums of them, or square roots, or exponentials, or anything like that? So one way to look at this is that everything you've done in your life in mathematics, all the rules you've learned are associated with numbers that are deterministic. If someone says a number has the value 6 and it has the value 6, what we're saying here is that's just a special case. In fact, all these numbers that you're always associated with, if they have any physical meaning, are always random. Because if you measure things, then if you make multiple measurements, you don't always get the same answer. If you conduct experiments like rolling dice or making a space shot. Everyone's talking now about the explosion of Columbia. Well, that's really a random process. You got all of these complicated things that are going on, and every once in a while enough of them go wrong so that everything falls apart. And what you're trying to do is you're trying to minimize the probability of that happening. It's very complicated. But the thing is that it is a random process, and that in the design, the engineering design of these kinds of things, you have to worry about doing things like adding the effects of the random components. So this will turn out to be an important point where we're going to be doing arithmetic with numbers, except that the numbers themselves have random values, not deterministic values. So anyhow, right here we can see that if I want to calculate the probability that the sum is equal to 8, I just have to add up count the number of points, 5, divided by the number of points in the sample space, 36, I get the answer. Suppose I wanted to find the probability that x1 plus x2 does not equal 8. Well, according to one of our theorems, the event x1 plus x2 does not equal 8 is the complement of the event that it does equal 8. So I could simply say that equal to 1 minus the probability that x1 plus x2 does equal 8. So that's 1 minus 5 over 36, which is 31 over 36. But we could check that directly, because we could go back to the sample space, and we could count the number of points that correspond to x1 plus x2 not equaling 8. Well, 5 of them do equal 8. There are 36 altogether, so 31 of these points do not equal 8. So this probability would be 31 over 36. So that just justifies that theorem. How about the event? Okay, let's go over here. Suppose I asked for this. Suppose I said, what's the probability that when I roll the dice that either x1 is equal to 5 or the sum of the two dice is equal to 8? Well, that's a union. That's A or B. So I can say, well, that's equal to the probability that x1 is equal to 5 plus the probability that x1 plus x2 adds up to 8 minus the probability of the intersection, which is that x1 is equal to 5 and, I indicate intersection by a comma, x1 plus x2 adds up to 8. Okay, so what's that? Well, let's see, let me erase this stuff here. This is the probability that x1 is equal to 5, which is 6 over 36. And here we have the probability the sum is equal to 8. Well, that is equal to 5 over 36. And now I have to subtract the probability that x1 is equal to 5 and x1 plus x2 is equal to 8. Now, that's an intersection. How could that occur? The only way that x1 can be 5 and their sum be 8 is x1 is equal to 5 and x2 is equal to 3. Because if this is true, then that's true. If that's true, then that's true. Okay, but what's this? That's just the probability of one of those points in the sample space. 6 over 36 plus 5 over 36 minus 1 over 36. That's 11 over 36 minus 1 over 36. That's 10 over 36. Okay, let's go back to the diagram here. We want the probability of the union. x1 is equal to 5. Or the event that the sum of x1 and x plus 2, and x1 and x2 adds up to 8. So the union of these points is a set of points that are in both. How many such points are there? 1, 2, 3, 4, 5, 6, 7, I don't want to count that twice, 8, 9, 10. 10 over 36. Okay? So it's all very simple. It all works out. So even though it looks abstract, there's nothing to it. Any questions about that? Okay, the intersection part is right here. I had to subtract the probability of this because I didn't want to count it twice. And so I have to make sure when I count the points this way and this way, but I don't count that one twice. Okay, so now where we stand, maybe we've done a lot fast, I don't know. But after you've gone back and read this and thought about it, there really isn't that much here. So where we stand is we've defined everything. We know how to calculate probabilities in simple cases. And you can see that basically if I want to calculate the probability of some event, what I have to do is I somehow have to add up the probabilities associated with sets of those events. So in something like this is simple because there's 36 points. I can simply draw the picture, count the points, no big deal. But I want to be able to answer questions where I can't count very easily. So for example, so here's the kind of thing we're going to do. Suppose that I want to calculate the probability that if I deal out a hand of cards, 5-card hand of poker, that a certain poker hand is dealt out. So I could say, for example, what's the probability that if I deal out 5 cards, that the hand that I get will contain 4 of a kind? So we're going to have to, I'll explain for some of you who don't understand this stuff about cards, what this means. But 4 of a kind means that among the 5 cards, there are either 4 aces or 4 twos or 4 threes or 4 fours or something like that. So from one point of view, this is really trivial because all I have to do is say, okay, how many different hands of cards are there? And if I assume that every 5-card selection is as likely as every other one, in other words, the deck is shuffled, then all I have to do to calculate the probability of 4 of a kind is count how many hands there are that are 4 of a kind, divide that by how many hands there are. That ratio is the probability of getting 4 of a kind. But how many different 5-card hands are there? Well, it turns out that there's about 2.5 million. How many 4-card hands are there? Well, I don't know how many there are. But the point is that what I have to do in order to answer this question is I have to count how many points there are in the sample space and how many points in the sample space correspond to the particular event. And so in order to do that, even though the theory is simple, the actual counting can be difficult. So I want to spend a small amount of time talking about systematic ways of counting. And this is something that you will have learned in a course in discrete math. So if you've taken discrete math, what I'm going to do next is going to be relatively simple. And if you haven't, then you'll learn it here. And when you take the course in discrete math, it'll be simple there. But there's some overlap between those two courses. Okay, I got 12, 11, 10, so forth seconds left. Any questions before we quit? Okay, so read these pages and have your questions ready, and I'll discuss this next time.